Well, welcome everyone. I can't say good afternoon anymore when we're doing video events because we don't know where everybody is all around the world. But welcome, I'm Rob Atkinson. I'm president of the Information Technology and Innovation Foundation. And we're really pleased to be hosting this great event today about how digitalization is affecting and really transforming global energy systems all around the globe in all sectors of our economy. And of course, now with COVID-19 pandemic, we're all using digital technologies more as we are right now with Zoom or YouTube, et cetera. IdeaF has long written about and talked about these issues, particularly as it relates to issues around digital manufacturing, automated and connected vehicles, smart cities, smart grid. And we wanted to host this event to focus on the energy impacts of digitalization. And most importantly, particularly about how digital technologies can actually save and optimize energy use and energy efficiency in a wide array of sectors. So I want to welcome you to this event. If you're watching it on the IdeaF website and you'd like to ask a question, please click the link to ask questions on the Slido. If you're watching it on YouTube, just follow the link in the event description and again, you can ask a question. So our keynote speaker who's going to kick us off today, we're really pleased to be able to host Andreas Erstwitz, who is with Infineon Technologies. And Andreas is joining us from Germany. If you don't know about Infineon, they're one of the top 10 semiconductor manufacturers in the world. They're a German-based company, but they have over 4,000 employees in the United States, including 26 locations of manufacturing and R&D in the US. They're a leader in automotive and power semiconductors and a really highly innovative company. I had the honor of speaking at this Infineon Oktoberfest that they do in Silicon Valley, and I have my Infineon beer mug to prove it, although I'm drinking water right now. And I always remember going to one of their engineer demonstrations where they were demonstrating these little chips, microelectronic MEMS devices that were so sensitive, they could sense when somebody stepped up 1 foot. In other words, they could tell you as you stepped up 1 foot, you were up a foot or 2 foot or whatever. It's incredible. It's almost like, as Arthur C. Clarke once said about technology, any really powerful technology is indistinguishable from magic. So really pleased to have Andreas with us. He's the division president of Infineon's Power and Sensor Systems. That division makes energy saving chips and sensors. Their products go in devices to make them more efficient, increase ease of use, and to make the devices more understandable and easy to use in their surroundings. Andreas joined Infineon in 1995 in product planning and strategy, and has held a wide variety of positions at the company before his current post of division president of power and sensor systems. So with that, Andreas, really looking forward to hearing your discussion.
Thank you so much, Rob. Thanks for the invitation. I'm almost tempted to say you made my speech. Nevertheless, I'm going to try my best in order to now illustrate to the audience a little bit what semiconductor technology I can do in order to help saving CO2 emission and make the world a bit greener. But before getting started, maybe just one final remark on me as a person, and thank you for your kind introduction of myself. So before joining Infineon Technologies, I used to grow up on a farm. So I'm a farming background, and why is that of importance? Farming is something where sustainability and so to say thinking in you have to get started with something at the beginning of the year, seeding in order to then later harvest and do it in a way that is so sustainable that you can continue doing so over generations. That is something actually which I got implanted into my DNA, and that made me then also at the very end decide to join Infineon and help Infineon cultivate, and not only cultivate, but then also realize this vision of energy efficiency and creating semiconductor systems that help driving energy efficiency and energy consumption reduction going forward. Let me come to the content of the speech. So technologies enabling the 2 degrees C climate goal of the Paris Agreement is the title. Let's jump straight into what it is about. Chart 1, let me get your attention into the overall world consumption of primary energy, which is equivalent to somewhat like 160,000 terawatt hours of primary energy. What is primary energy? That pretty much contains oil, gas, coal, but then also renewable energies such as wind, hydropower that are converted into electricity directly. The interesting thing is that when you look into how much of the world primary energy is being consumed in the form of electricity, we are talking about more than 1/3 of the global energy consumption happening in electricity as of today. The tendency of that share to increase is rising while we speak. So far, so good. The interesting thing to know in that context is that the 17 percentage points, so if you look into the green part of the pie, where electricity is generated out of fossil primary energy carriers, the average efficiency of primary energy used for that is only 50 percentage points. And that means, if you translate it into other words, that to come up with electricity accounting for a little bit more than 1/3 of global energy consumption, it takes another 17 percentage points of primary energy in terms of coal, gas, and also oil that needs to be burned to create that energy and to create that electricity in the greenish part of the bar. So having said that, saving electricity, as you can imagine, and saving each and every kilowatt hour of electricity makes a lot of impact with regards to CO2 emission. Also noting that according to data underlying, where we are making our calculations based on, 1 kilowatt hour of electricity in average creates 490 grams of CO2 emission. So there are enormous savings potentials as soon as it gets towards considerations on saving in electricity. And semiconductors are very important technologies that enable energy savings. And I give you later a couple of examples on what it concretely can be. Infineon as a company is working alongst all three major drivers and contributing that help to reduce the consumption of energy or reduce the creation of CO2 emission, if you will. Point one, we are working on developing and manufacturing semiconductors that enable renewable energies to work. So every windmill, for instance, has a motor and has a electronic AC to DC or DC to AC converter that is then turning wind energy into current and voltage that is being put into the grid, enabled by semiconductors made by Infineon. But Infineon is also working on a bunch of semiconductor technologies such as sensors, microcontrollers, and also power semiconductors that help increasing the energy efficiency of each and every electronic device. So you consider like this, each and everything that needs power, and we have many, many different applications and devices around us that are run by power, current and voltage are floating through cables, sometimes also wireless. Infineon is working on semiconductors that help reducing the efficiency losses while power and voltage is being converted and put towards the load that is then consuming power. A load is something like, for instance, the laptop you're using right now in order to participate in the Zoom meeting. And last not least, other than manufacturing technologies that help reducing power consumption, Infineon is also contributing and putting a lot of effort into reducing its own CO2 footprint, because a bit critically speaking, while being in all these manufacturing activities and doing the production of semiconductors, CO2 is emitted. And we have put a program in place that aims to make Infineon CO2 neutral until 2030. And I'm going to share with you how that can happen and what's the plan behind, because I believe that many other companies can also get an input or eventually even learn from that what we are doing. Coming to a couple of selected examples on semiconductors driving energy efficiency when it is about electricity consumption. Let's get started with the smart home. So converting a standard residential home to a smart home, what's in, what can be saved going forward through the use of modern semiconductor technologies. First, round about 29 percentage points of the worldwide electricity consumption are consumed by residential buildings. That's enormous, and having said that, everything that can be saved meaningfully within buildings obviously has an enormous contribution in terms of CO2 emission reduction going forward. When you look into what is then, so to say, driving this energy consumption in residential buildings, the top drivers in the US, according to underlying data, are space cooling, so air conditioning and climate conditioning equipment, 16%, space heating and water heating amounting up to 27 percentage points of that consumption. Refrigeration typically takes 6 percentage points in an average household. Lighting is somewhat like 5 percentage points. So these are main drivers for energy consumption. Going forward, by the use of semiconductors, what can be saved out of this? And let me guide you through that picture. On the top, you can see the key issues of heating the house, cooling the house, and lighting the house. Through use of smart thermostats, for instance, pardon me, that contain temperature sensors and connectivity devices, but then also microcontrollers. Through that, you create an impact into the heating control of your housing, the cooling control of your housing, and that helps you per se reducing the energy consumption through smarter cooling or heating. Key for this is, if you will, smart sensors and microcontrollers who do the work on telling the sensor how to react in certain conditions. Second point is remote control, which is enabled for all of us using our smartphones, for instance, being always connected in the internet and through the internet get connectivity also to our heating and cooling equipment. Also smart and remote control helps to reduce heating and cooling energy consumption. As a matter of fact, by switching off and on the cooling and heating equipment when you're not at home or when you're at home. The other topic are occupancy sensors, for instance. So by the consequent use of occupancy sensors such as radar devices who tell electronic equipment such as your cooling or heating or also lighting equipment that you're at home or how many people are in a room, also that allows a much smarter air conditioning or heating or also lighting independency of is there somebody in the room, how many people are in the room, and if there's nobody in the room, of course, all these devices can regulate energy consumption down. Smart power supplies. So these are power converters that turn alternating current into direct current, so electricity from the grid into a DC as it's being used by each and every electronics. That, of course, has an impact on power consumption of your air conditioner, of your heating system, of your lighting system, and of each and every device that you're using in your household. Also, televisions use a power supply, and depending on the semiconductor technologies that you're using in the television power supply, the thing is consuming power in standby or not when it is in standby. So smart technologies in the form of semiconductors help reducing standby consumption as one example. And last not least, motor control and smartification of each and every motor as it's being used in cooling equipment, as it's being used in heating equipment. Also, motors need to be controlled in an efficient manner. Therefore, you need power semiconductors, you need microcontrollers, you again need connectivity. All this is semiconductors that then help driving, making a motor, like a motor for your refrigerator or the motor for your air conditioner, much more efficient when it's about power consumption. All in all, when you sum it up, this sensorification and digitalization of a smart home can save, depending on the starting point, in between 30 to 50 percentage points of energy in your home. And again, when you calculate it back and calculate how much that reflects in terms of CO2 emission, it's, let me jump back to the other slide, probably 30 to 40 percentage points of the 29 percentage points of electricity consumed in CO2 equivalents. Okay. Let me give you a second example. I'm now going to talk about the age of data processing, where the situation, the starting point looks as follows. So in contrast to residential buildings, information communication technology as of 2018 account for 4 percentage points of electricity consumption worldwide. That appears to be not that much and that impactful, but going forward, the demand and power consumption predicted for ICT is gonna exponentially grow unless we start acting and put means in place related to energy efficiency and the use of energy efficient technologies. So why, so to say, this demand of electricity for ICT is gonna increase is shown on the next chart. Let me share with you that as of today, only 50% of the world population are connected to the internet. Trend growing, of course. The average per person data usage is 1.7 megabyte. Going forward, that's going to increase. Mobile device data increased by 40% through 2018 to 19. If you just look into Q1 to Q2 comparison in 2020, when COVID happened and all this streaming and Zoom conferencing was skyrocketing, if you will, there was another increase of data consumption in the average in Europe. So here we have data points by 40 percentage points in the quarter of COVID relative to the previous quarter. So we see that data traffic is increasing heavily, and data traffic and management of data traffic is power hungry. Why is it power hungry? You need a lot of data centers in order to kind of manage something like a Zoom conference as of today, point number one. And you need a lot of communication infrastructure, bandwidth, but then also wireless macro base stations and towers, for instance, in order to, on a mobile manner, then enjoy participation in a video conference like that of today. So everything of that equipment, data centers, ICT equipment, if you will, is power hungry. Going forward, the prediction is that until 2025, there's going to be an exponential growth of the data rate that is going to be managed in the cloud, if you will, and transmitted through whatever kind of telecom equipment. So some can assume that unless energy efficient technologies are being put in place, so for instance, in order to make a given data center less power hungry, and I come to an example, we're going to run in a problem in terms of electricity consumption as it will happen by data centers, ICT equipment going forward. Let me give you a concrete example, what semiconductors can help saving in the case of applying some in principle consideration and use of a new semiconductor material called gallium nitride in each and every US-based data center as of 2019. Gallium nitride is, I don't want to go too much into detail, is a novel semiconductor material that helps to revolutionize energy losses when voltage and current are being switched, and so to say electricity is being taken out of the grid and fueled towards a server processor. When that power flow happens, typically heat is dissipated due to energy disefficiencies, if I may say. By the use of gallium nitride in each and every data center in the US, keeping everything else the same, all of a sudden 4 billion kilowatt hours of electricity can be immediately saved. That equals $300 million of energy cost. And that again equals somewhat like 2 million tons of CO2 emissions lesser per year. That's a very simple example in order to illustrate what semiconductors can do, in that case in a data center. And in that case, using a new semiconductor material like gallium nitride, that has a huge impact in terms of CO2 emission reduction or avoidance of CO2 emission going forward. In that context, Infineon is also participating in a research project together with the ARPA-E. It's related to gallium nitride, what I mentioned before. And this basic research has the aim to develop a new class of ultra-efficient, lightweight, and also ultra-reliable power converters through the use of gallium nitride. That in principle research and manufacturing, by the way, is happening on our manufacturing and research plant in Mesa in Arizona, and helps us, and I think helps the society forward looking to put novel technology in place, in that case coming out of the US, to further reduce energy losses when energy is being consumed. I give you a third example, and here we go into, from a product view, related to Infineon's product portfolio and technology contributions towards what can we, as CO2 emitter, as a company do in order to reduce our 1.4 million tons of CO2 emission as of 2014. And let me share with you the following consideration. As I meant at the beginning, so Infineon plans to be CO2 neutral by 2030. So another 10 years to go. You may say, oh, that's a long period of time. When you look into details, it's aggressive, I dare to say. So far, Infineon has defined measures to reduce 70% until 2025 of this CO2 emission. And here comes the question how we are doing this. And there's a couple of measures that are put in place. Let me share with you. We have a program in deployment where we consequently deploy exhaust air purification systems to reduce or minimize greenhouse gas emissions throughout our manufacturing plants. Second point, we improve and work on energy efficiency ourselves by migration of our manufacturing sites towards the most modern process technologies. What's behind? We are using a new machinery that is more power efficient, that has higher power efficient power supplies on the one hand and can create the same output of manufacturing volume through the use of lesser energy or using the same amount of energy, more output simply. Third point, we switch to 100% green electricity. So that's something which is feasible in Europe. So buying energy that comes from renewable. So Infineon is deploying a plan to become 100% green electricity consuming until 2025. We're also promoting electromobility with our car fleet, if you will, for employees on the one hand, but also by building up and providing charging infrastructure on all of our sites. And last not least, for everything where CO2 emission cannot be avoided. And that's the case, for instance, by the use of a couple of gases in our manufacturing processes. We're deploying a plan to purchase CO2 certificates. Let me sum it up. Reaching the 2°C climate goal of the Paris Agreement, I guess that's a social responsibility for all of us, and also for Infineon, for me as a company representative, not only also as a private person going forward. So we work on reducing our CO2 footprint wherever we can. Modern semiconductors are a main contributor, as I've mentioned before, in order to achieve that goal. Close collaboration between industry and policymaker, however, is a key to success going forward. And what it takes, industry to collaborate with policymakers in order to put means in place that help to accelerate energy saving means, that I guess we're going to discuss in the coming 1 hour or debate to happen. And last not least, everybody can and must do their part to reduce the CO2 footprint globally. I'm through it. Thank you very much. And I herewith hand over back to Rob.
Andreas, thank you so much. That was great. And, you know, one of the, I think the points that you made there, what I thought was interesting, was that these technologies are being used not just to reduce energy in things like motors or refrigerators or, you know, smart lighting, but they're actually being used to reduce energy in IT devices themselves, like cloud centers and all. So that's a perfect segue into our next speaker, Colin Cunliffe. Colin is a senior policy analyst at IdeaF. He focused on clean energy innovation. If you haven't read Colin's work, it's on our website. It's fantastic work. Really, I think, has broken ground in a lot of areas, particularly hard to decarbonize sectors. Prior to joining us, he had been at DOE's Office of Energy Policy and Systems Analysis Group, and he holds a PhD in physics from University of California, Davis. So Colin, take it away.
Thank you, Rob. I'm gonna, share my screen. And whoops. Okay, is that good? Can you all see my slides? Okay, perfect. So again, my name is Colin. I'm a senior policy analyst here at IdeaF, where I focus on clean energy innovation policy. Now, I want to remind people to submit questions to the panel on our website at ideaf.org/energy efficiency, or if you're on YouTube, you can just follow the link below. So now IdeaF has written a lot about digital manufacturing and intelligent transportation systems and other applications of IT. And we just released a report this week that was motivated by the desire to understand the energy and climate impacts of information and communications technologies. So that includes both the energy and carbon footprint of the IT sector itself. That also includes the impacts of IT on energy use in other sectors. And you can download this report at ideaf.org/energy-techlash. So when answering the first question, one of the things we found is that there's actually a lot of misinformation out there. We've seen headlines that YouTube views of the music video Despacito consume as much electricity as 5 African countries. And that's not right. This kind of misinformation does nothing to further the conversation. The ICT sector is an important energy consuming sector. It does need to decarbonize just like other sectors, but misinformation really doesn't help. So I begin with the report just by going through some of these common misconceptions that have appeared in mainstream media and fact checking some of this. So I'm not going to do all of this here, but I do want to go through this Despacito claim. So the claim came about because Despacito was the first music video to reach 5 billion views on YouTube. And it is based on this idea that 5 billion views consumes 1 terawatt-hour of electricity. Now, this can't possibly be true because YouTube, 5 billion views of Despacito is equivalent to about 0.4 billion viewing hours. And YouTube receives 1 billion viewing hours every single day. So for this to be true, YouTube viewing over the entire course of the year would have to consume 930 terawatt hours of electricity, which is more than 4 times more than all of the electricity consumed by data centers around the globe. So a much better estimate is that Despacito, 5 billion views, consumes about 0.005 terawatt hours. This isn't the only wild claim. So we have produced this report. We hope that it can serve as a resource for people and for the media who have questions about the impact of video streaming and other digital services. But this might at least appear plausible to the casual observer because our experience is much like what Andreas described. We are consuming more data. We have more connected devices. And that may be why some of these sensational claims have such cachet. So we wanted to get at this question, what is the real energy and carbon footprint of the ICT sector? Again, like all sectors, it will have to decarbonize. We find, similar to Andreas, that ICT accounts for 4% of global electricity demand. And that's about 1% each for data centers and data transmission networks, and 2% for consumer devices, for smartphones and smart appliances. And this comes out to about 1.4% of global greenhouse gas emissions. So that's not negligible, but it's far below heavy industries such as iron and steel, chemicals, and cement manufacturing. And the International Energy Agency comes out with their annual Tracking Clean Energy Progress report. They actually identify data centers and data networks as one of only 6 key technologies and end-use energy sectors that is on track for a 2-degree scenario. The reason they have come to this conclusion is that even as demand for data centers have been growing exponentially, rapid, equally exponential improvements in efficiency have helped keep energy demand flat. And their determination is that that is likely to continue at least into the next couple years. But also tech companies are decarbonizing their electricity supply faster than the grid as a whole. So they are procuring clean energy, they are procuring more renewable energy than other big companies. And then finally, the International Telecommunication Union was the first union to work with the Science-Based Target Initiative to develop industry-wide standards that are science-based decarbonization targets. That just came out, that just happened in February of 2020. So this is really impressive commitment from the IT sector as a whole. And I want to dig into this first question. Again, I think we all have this tangible experience of data growing rapidly and its importance in our lives. So between 2010 and 2018, for example, data center storage capacity increased by a factor of 26. Data center internet traffic increased 11 times, and data center workload increased by more than 6.5 times. But despite this, computing efficiency has doubled every 1.6 years. This is a phenomenon known as Kuhne's law. Storage energy intensity decreased to 90%. And then the average power usage effectiveness of data centers, which measures how much of the electricity data centers consume that goes to running their servers versus cooling, lighting, energy procurement, and other services. That has decreased by 25%. So the end result you can see in this gray line is that data center energy usage has actually remained pretty flat over the past decade, even as these services have grown exponentially. So in 2010, data centers consumed 194 terawatt hours of electricity. In 2018, they consumed 205 terawatt hours, a 6% increase. But global electricity demand grew much faster over that same period, with the result that the share of electricity consumed by data centers actually declined over the past decade. And then again, this is reporting from Bloomberg New Energy Finance and the International Energy Agency. Tech companies and communications technologies in the past few years have actually been leaders of corporate procurement of renewable energy and have accounted for about half of global procurements across all sectors. So that answers the first question, what is the energy carbon footprint of IT? Now, the full energy and carbon footprint includes not just the energy impacts of IT, but how it impacts energy consumption in other sectors, and particularly how it can optimize and improve efficiencies and improve smarter use of energy so that we're consuming energy when and where it is needed. So that's the second half of this report. I can't possibly be comprehensive. This is a 20-page report. It should be a short read. But I do want to go through a few examples. Andreas already talked about smart buildings, so I'm going to skip this, except one thing to note is that in addition to reducing the energy consumed within buildings themselves, smart buildings can also integrate into the electricity grid to provide additional systems level efficiencies. So they can provide demand response, they can enable shifting or shedding load during peak consumption to periods where electricity is less expensive. And this can actually avoid expensive build-outs of natural gas combustion turbines, or so-called peaker plants that only run for a few hundred hours out of the entire year when electricity demand is highest. Now, IdeaF has written extensively on digital manufacturing and the many benefits that provides to productivity, to worker safety, to improved product quality. And I'll refer you to our exhaustive work on this topic. But I do want to talk about the energy and environmental benefits of digital manufacturing. So industrial facilities account for 38% of global final energy consumption, 32% here in the US. And there's really a huge potential of energy that integrating IT, integrating smart sensors, automation, and artificial intelligence into manufacturing can achieve. So the US Smart Manufacturing Leadership Coalition, for example, projects that greater integration of IT can improve energy efficiency by 25%, can also reduce packaging, and can also reduce the water use in manufacturing. Other reports from McKinsey, for example, or also from the American Council for an Energy Efficient Economy have reached similar conclusions that digital manufacturing has enormous potential to reduce the energy intensity of manufacturing. One thing that I'm particularly interested in is the application of digital manufacturing and the application of IT in some of the heavy industry and some of these harder to decarbonize sectors. So these are sectors where there are no commercially available low carbon alternatives. And it's really going to take decades to develop new low carbon options and scale them up to commercial scale at a cost that is viable. So in the interim, efficiency is one of the few levers we have to decarbonize these sectors. And I'm talking about cement, iron and steel, chemicals. These are all very hard to decarbonize sectors. And digital technologies are going to play a key role in maximizing that efficiency. So I profile cement for just a minute. Lafarge Holcim, which is one of the world's largest cement manufacturers, they just announced a new initiative last year to use digital twins, automation, and machine learning and robotics to improve the energy efficiency of their 270 cement factories worldwide by about 15 to 20%. So that's a huge chunk, again, when we're talking about a sector where there are very few other options. Argos is one cement manufacturer. They're partnering with the US Department of Energy and the University of Louisville to also to reduce the energy intensity of clinker production, which is a key step in the cement manufacturing process. And then Pedum is a company that is using artificial intelligence also in the cement manufacturing sector. Other applications in transportation, again, there are a lot of near-term options to decarbonize light-duty vehicles like cars and trucks. But it's going to be really important for heavy transport for things like aviation, shipping, and long-distance freight transport by trucks. These are sectors where there really aren't good options, at least in the near term, where the energy density requirements of their fuel is such that they are going to likely continue to rely on petroleum-based fuels for the coming decades. And as we scale up new low carbon alternatives, efficiency is one of the best options for reducing the energy and carbon footprints of these sectors. So I think I'm about out of time. I don't want to go into all of this in detail. Maybe we can get into this in the panel discussion. But I do want to turn it over to our panelists now. I just want to conclude by saying that the energy and carbon footprint of information and communications technologies is manageable for now. The sector is doing a lot to decarbonize. Of course, like all sectors, it faces challenges. But then I also think there's a tremendous opportunity to use digital technologies to help other sectors address their energy and carbon footprints. And with that, I'm going to turn it over to Javed, our moderator.
Thanks very much, Colin. Yes, so I'm Javed Ouma. I'm a policy analyst here at IdeaF, and I'm very happy to be moderating the remainder of this session. And I'd like to start by introducing our two other panelists, starting with Clay Nessler, who is the Vice President of Global Energy and Regulatory Affairs at Johnson Controls. We're very happy to have you. And I'd like to hand over and ask you to provide some comments on this topic.
Great, thank you. And thanks to ITF for inviting me to participate in today's webinar. What an important topic for us to be discussing, the role of digitalization to support our decarbonization and other goals. I'd like to just mention that in addition to my Johnson Controls role, where I've worked for 37 years, I'm also the interim president of the Alliance to Save Energy, which is a 43-year-old energy efficiency nonprofit based in Washington, D.C. So I'll be pulling from both hats, if you will, in today's webinar. Throwing some more data at an already data-intensive presentation. For 13 years, Johnson Controls has held a global survey of commercial, institutional, and industrial facilities talking to their facility and energy management executives about their investment trends. A couple highlights from last year's survey, which, by the way, was completed late November, early December. Those dates will be important as we advance through time. The good news is 25% of organizations in the US plan to increase investment in energy efficiency and smart building technologies. And we use smart buildings to kind of talk about the digitalization of buildings. 2/3 of organizations plan to make investment in building controls. 50% plan to integrate their building systems together into a common network, sharing data and implementing advanced automation and other functionalities. And 50% actually plan to invest in demand response and demand management type of capabilities. Thinking about systems integration, this is a new and upcoming area where predicted for this year, 83% plan to integrate their security systems with other building technology systems. 70% their fire and life safety. Imagine a fire alarm being wired into a HVAC unit such that the floor above and below a floor with a fire alarm could be pressurized to isolate smoke and allow people to egress the building safely. One of the many examples of by digitalization and tying building systems together, we can both be efficient and more safe. Over half are integrating lighting, building management. Equipment is getting smarter every day. The opening presentation talking about the smart appliances and equipment in homes for heating, cooling, and others are just an example of how every device in buildings is becoming a network connected intelligent device. And really it's providing functionality at 3 levels. The equipment itself is getting smarter, allowing it to be more efficient and operate better as a systems component. Those systems and equipment within buildings are integrated together to provide greater functionality. And as Colin mentioned, the ability of buildings to integrate to the electric grid, an increasingly modernized and digital electric grid, provides the capability of being able to shift demand, flex, if you will, and not only consume electricity like we have for 100 years, but produce, control, store, and manage energy to provide services to the grid. NASIO and NARUC, energy officers and regulatory commissioners, have been working together in a working group to really try to drive this movement, which DOE has been very actively in supporting. It's a very exciting trend. A couple things driving this, I believe. One is the trend towards net zero buildings. One of the first large net zero carbon commercial buildings is in Silver Spring, Maryland, close to where I live. And they were quoted at the end of the project, which is in fact net zero, that controls weren't even on their mind, or smart building systems when they started the project. Ended up living or dying based on the integration of these digitalized and smart building technologies. It was absolutely critical in being able to get the energy use down to a level which could be met through renewable energy, geothermal heat pumps, and things such as that. We tend to think of this as, in order to decarbonize and meet the Paris objectives by 2050, we need to electrify. We need to electrify and decarbonize the grid. We need to electrify heating in buildings. We need to electrify transportation, and we need to electrify manufacturing processes to the greatest extent possible. Well, that sounds easy, but it's not. And if we electrify everything, we're going to see some huge changes. In the United States, we may very well go from peaking electricity use in the summer with air conditioning to peaking electricity use in the winter. The bad thing about the East Coast of the US, where I live, is in the winter we have things called polar vortexes. Imagine a polar vortex hitting a whole bunch of electric heat pumps at the same time could put an incredible demand on the grid. In order to be able to electrify the built environment, we're going to need it to be much more efficient at a building and an equipment level. And in order for these buildings and their equipment to actively support the grid and not require tons of new transmission generation and distribution, we're going to have to digitalize. This equipment in these buildings are going to have to be smart and be able to operate on the grid to shift loads and help manage the grid. Otherwise, it will have to be a lot larger and a lot more expensive than it is today. The last driver coming is what's the impact of COVID? After this survey was done, this funny little thing, not funny at all, called the COVID-19 pandemic, basically shut down buildings. Buildings are empty today. It's just tragic, the impact that it's had on the world and on the built environment. It's very interesting to note that despite the fact that all these buildings are empty, they're still using 70 to 80% of the energy they did before. That is a big deal. And what we find is that the same technology that's required to make a building net zero, being able to reduce loads, to match the conditioning to individuals, to actually be able to flex the operation of the facility. What we would do for net zero buildings is exactly what we need to do post-COVID in the new normal, when buildings will be occupied over longer hours, they will have less occupancy, they may operate 6 days a week instead of 5. So we need more digitalization technology rather than less in order to address the new normal. We recently had a webinar at the Alliance to Save Energy. It was sponsored by the Digital Climate Alliance. And we talked about our active efficiency initiative, where we've combined energy efficiency, traditional classic energy efficiency, with digitalization in order to provide more systems level and dynamic control of buildings and other end uses to be able to live in this new digitalized world. So that's a very exciting area for us, and I look forward to the discussion. Thank you so much.
Thank you very much, Clay. And our final panelist is Ed Reiter. Ed is the director of the industrial program at the American Council for an Energy Efficient Economy, ACEEE. So I'd like to invite you, Ed, to provide your comments.
Okay, let me just do an audio check. Hold on, can you hear me okay?
Can hear you great.
Yeah, perfect. Well, thanks so much for the opportunity to speak, and kudos to Colin and his colleagues at IdeaF for an excellent report on a very timely topic. Now, ACEEE has been looking at what we called intelligent efficiency for a number of years. That is understanding how automation in IT can help interface with efficiency. And it's important in this regard to note how to take data to knowledge and then use that knowledge in an automated sense to improve performance. This is particularly important in the heavy industries that Colin had mentioned, because oftentimes energy efficiency improvements aren't suitably justified just based on their energy benefits. Often it's the non-energy benefits, improved yield, productivity, quality, etc., that justifies those projects. Hence, as we look at IoT and the ability of artificial intelligence, machine learning, and other to take that data, transform it into knowledge to improve performance, it's crucial for this delivery of those non-energy benefits and the justification of technologies such as further electrification. So ACEEE today, this afternoon, is coming out with a report on beneficial electrification. A beneficial being that electricity provided by low carbon sources, such as renewables. For that to occur, that electrification to occur, the challenges will be many, such as understanding the best applications. One of the big application areas, just to give an example, is process heat. And there are several different ways that heat can be provided. And for low and mid-range technology, low and mid-range temperature areas, there are several electric technologies such as heat pumps, as Clay had mentioned. For those to really be applied very, very efficiently, it's crucial that the understanding between technology and the ability to use the data and to improve performance is fully executed. Now, Clay had mentioned that it's quite likely that the energy usage will climb dramatically if industry really picks up on electrification. Well, it's crucial then that it's recognized that energy efficiency can help to reduce that increased demand by 50% or so. Hence, efficiency needs to go hand in hand with these efforts to further digitalize the use of not only data, but the performance of the machines. As I think about the performance of the machinery in the heavy industry in particular, I'll note that smart manufacturing is a concept that's really, really important, because smart manufacturing can improve the ability of machinery in heavy industry, motor drives, for example, to be used efficiently. And smart manufacturing platforms, such as that generated by SESME, the Smart Manufacturing Institute in the US, provide the ability to leverage profiles of different technologies from one instrumentation unit to another. In other words, once you figure out that smart manufacturing profile, it's leverageable to all similar units, nationally, worldwide, which provides a great opportunity for, again, efficiency gains. So again, I'll just wrap up my comments saying that we really appreciate the report. It's made a significant contribution to the conversations in this space. It draws all the right connections to efficiency and smart manufacturing, and the ability to look at data that's real and to find useful solutions in this challenge to decarbonize industry and other sectors.
Thanks very much, Ed. I'd like to invite all our panelists into the conversation. And I'd like to start by asking, we've spoken a little bit about the opportunities for digitalization of smart buildings, but are the opportunities for digitalization for smart homes or smart factories different for new versus existing facilities? And are there any additional challenges to retrofitting existing buildings? Anyone want to jump in?
I guess I'll jump in on the industrial sector and let Clay or others comment on the buildings. Retrofits have a really high hurdle relative to the return on investment for capital. But one of the things that I think is unique about this present situation is that the IT capabilities provide ability to get improvements and to look again at those non-energy benefits without changing out the pots and pans in industry. Since that's the case, it may provide a lower hurdle for some of these retrofits. You may be able to use the same equipment by just improving the IT and the ability to process the information downstream.
I think you're muted, Clay.
Sorry. Yeah, I would just add that a digitalization strategy in buildings or industry doesn't need to be a rip and replace strategy. One of the most exciting areas is the use of digitalization, machine learning, data analytics, and IoT sensing to put a digital overlay within an existing facility or a manufacturing plant. At one point, we had over 300 manufacturing plants around the world, and which allowed us to do some interesting experiments. One of the experiments, as we were implementing ISO 50001, an energy management system, in some plants around the world, and particularly in Europe, where there were tax incentives to do that, we also simultaneously put in sub-metering, where we would meter at an individual process and equipment level, hundreds of sub-meters within the plants. And what we found is that those facilities where we had interval meter data, at least 15 minutes, we used data analytics, we used fault detection and diagnostic software to identify problems, and we wrapped a process around it. We found about twice the annualized energy savings as we did in facilities that either had just a process or the data analytics. So I think that the new digital technologies offer an opportunity to upgrade existing facilities without having to get the dumpster out. And that'll certainly be a more cost-effective solution.
Thank you. We also have questions submitted from our audience, and one of them is for you, Andreas. What role will wide bandgap components play in the digitization of the electric grid and its components?
The two elements, digitalization of the grid per se. So as far as that one is concerned, wide bandgap as such is not a main contributor. So digitalization in something like a smart grid that is more a function of more intelligence and also better algorithms and software for grid balancing and things like that, which is in the make. So said that this portion cannot be addressed by wide bandgap technologies. What can be addressed by wide bandgap, however, is each and everything in terms of electronic devices, which is converting electricity and is converting, for instance, alternating current into direct current, such as it happens when electricity is taken from the plug, like in your home or like in a data center, or the data center takes electricity from the plug. And this alternating current needs to be converted into direct current and put towards and floated into something like, for instance, a machine learning processor. And that sort of power conversion and power converters that use wide bandgap based semiconductors. And here, a wide bandgap makes a major impact with regards to energy savings, while the conversion from AC to the DC is happening. So in terms of quantification, I was trying to give an example before in my speech, so no need to repeat that one. But having said the whole thing from another side, so once you use gallium nitride-based power flow in a data center throughout the entire chain, including, so wide bandgap, including smartness in the way how load management, data load management, cooling systems work, it has been shown by Colin that all in combination then starts making a lot of sense with regards to energy reduction and consumption reduction possibilities, ceteris paribus, so at the same amount of data management in a height of 20 to 30 percentage points savings per year. So it's a composition out of wide bandgap and a couple of other means in order to achieve the big saving.
Thank you. Around digitalization and manufacturing, Clay, Johnson Controls manufactures a lot of equipment for heating and air conditioning and refrigeration. Can you talk about how Johnson Controls has incorporated digital technologies to reduce its own energy carbon footprint?
Yeah, so the anecdote I mentioned earlier about including using data analytics and using that to monitor our manufacturing facilities has been one of the key things driving the reduction of our greenhouse gas footprint. That metering was really effective because we actually metered at a process step level. So a heating process step, then a forming process, then packaging. And what it allowed us to do was to benchmark the actual energy use per process step across similar facilities all around the world. One of the great uses of data is to be able to benchmark yourself, find the best of the best, make that the standard, and then drive improvement in all facilities to be able to achieve that. And I think using data in that way really allows the engineering plant floor employees to look at the data in real time and make adjustments and optimize. Optimizing buildings and manufacturing plants and everything isn't just technology, it's the integration of technology, process, and people. And where we've had high performance teams and where we've had effective use of visual elements within the factory floor is where we've seen the greatest savings.
Thank you. And Ed, what about the potential for digital manufacturing in the chemical sector or other hard to decarbonize industrial sectors?
The industrial sectors typically have not tapped into variable power. However, that's an opportunity. For some chemical processes, you could make various materials with variable electricity, and then you could stockpile it until you're able to go forward. An example, Colin had showed cement, and the generation of clinker is something that could be used with made with renewable power. It could be stockpiled and then moved further on. I think the industry sees this as an opportunity, however, to learn how to better use variable power. And I think electricity and the digitalization could particularly help with that to make that most effective. This is something where I believe also storage will come in, because storage can buffer that variable power supply. In doing so, the efficiency of that power will be very, very important to interface with the storage capabilities. And last, I would note that as industry looks at this potential, one of the things that's really interesting is, again, efficiency, because efficiency can help to lower some of the barriers and hurdles for these technologies that today are pretty expensive.
Thank you. I think we have just time for just one more question, unfortunately. And Andreas, I understand that last year the research building at Infineon Austria, the Austria site, developed a digital twin to reduce its own energy efficiency. Is this measure important in helping achieve Infineon's goal, as you said, of becoming carbon neutral by 2030?
Absolutely, and not yet clear with regards to the entire impact. So we're still awaiting a couple of more data points to compare its savings. But coming back to the content, I find it pretty much interesting because what we're doing in this digital twin program is as follows. So with the use of CO2 sensors, the use of humidity sensors, the use of temperature sensors, coupled with, so to say, temperature measurement outside, including weather predictions going forward, there is a machine learning running behind, which actually determines at each and every point in timing the optimum operating temperature for a room. And some has to know the optimum operating temperature for a room is not necessarily the air temperature in a room, but this is rather a function out of the temperature of the walls and their heat or cold dissipation, including then, so to say, the air temperature in the room, humidity, and outside effects that all blend into human feel well at a certain point in timing. And out of, so to say, fusing that data points by the use of sensors, including AI, we're working on optimizing the regulation for heating and cooling in this building. And going forward, the expectation is to reduce power consumption by another 20 to 40 percentage points. That's the plan. And that, of course, contributes strongly going forward towards Infineon reaching its ambitious CO2 reduction goals.
Thank you so much. We've actually somehow blasted through the hour already. And I'd like to thank all of you for joining us today, for your great insights. And I want to thank all of our audience who joined us and encourage you to look at all the material and reports that have been mentioned today. And just a great thank you to you all.